well, it's not
A little milky.
I better.
You know how many weeks in a row I've been sitting and I'm
I mean,
like,
that makes
dang,
sense.
I want a milkshake.
I'm saying
It's
just
30
something
minutes
check
from
it, leave it,
anybody that's
and
got a
see.
milkshake.
I'm a dork, I know, it's okay.
Just for that, I'm putting a funny name on it.
I tried to tell Dr. Nas that you take attendance like this and then you should try it, and he said it has to be too difficult.
Just tell me not to.
He said, I don't know how to make a QR code.
I don't need Dr. Nas old school.
Apparently
The website is QR code generator. Now look, yeah, everybody's gotta do their own thing. Nothing wrong with that. Okay. I think 2.5 is graded. I'm not sure it should be, but if not, I will check and see. I know 2.5 and 2.6 were what the TA was working on. Just so everybody's aware, so homework 2.7 is due today. We only have 2 more assignments between now and the next celebration, for the first celebration. So just so everybody's aware, we celebrate next Friday. So Monday, you're going to submit homework 2.8. Wednesday, you're going to submit homework 2.9. Now, I'm going to give you the solution to homework 2.9 on Wednesday so that you have it in preparation for the exam. There's no late submissions, therefore, on the homework assignment that's on Wednesday. Okay. My exams in here are very much like my exams in my previous classes. And one thing I'll say about my exams in steel design, you've all had me for class before, and you know that one of my policies is that I don't really like comprehensive exams. But I have said that sometimes the material bleeds over from exam to exam, but my exams I don't really intend to be comprehensive. This class is really where all that came from, because these exams really are not comprehensive. I mean, this class is very modular. Like after we get finished with tension members, we're moving on. We're talking about bolted connections and welded connections. And while there are some similarities, they're different. Like they're different topics. So the next exam will be on something different. Sound good? All right. So I'm going to give a quick recap of what we talked about last time, and I want to kind of get into our example and specifically how to identify block shear failure paths. And I've got some three-dimensional renderings, which might make it a little easier to see it. Once you see it, you kind of have seen it, and that's it. But I think the 3D aspect of it will make it a little easier. So it would help if I plugged this in. So we're talking about block shear, which is again this combination of a tensile failure and a shear failure, where one of the paths of a connection, or one of the paths around the steel, around a connection, will experience a shear failure. One of the paths will experience a tensile failure, and it results in just that, a block of steel essentially getting ripped out of the section. Okay. What you're seeing here is an example of a block shear failure path where the block, if you will, the green region, contains one shear path and one tensile path. I really need to use a different color for the shear. I don't know, I can't read that at all. Maybe I'll make it red or something, I don't know. But yeah, you can see the two edges of the block on the left, on the upper and the lower part of the block here on the slide are experiencing shear, and then the edge on the right is experiencing tension. So that the block is experiencing a combination of a tensile shear failure. Yes, sir?
I was just going to say, so basically just perforates it, so then it you can tear it easier.
Basically, just like there on the top right, the whole block, it just rips out, and what can happen is you can have a central block rip out, or, and we're going to talk about this a little later today, is you can have like a section on the bottom right, or on the bottom left, get ripped out. And we're going to talk about how to identify those paths here in a bit. Okay. The equation in the spec is one of a class of equations that's probably written a little strangely the first time that you see it, because if you look at it mathematically, it is Rn equals an expression such that it is less than or equal to another expression. And that looks a little strange the first time that you see it, but really what the spec is just saying is that it is the minimum of those two quantities. And you'll see that type of formatting in various structural specifications like the steel manual, which we're using now. You'll see it in places like the bridge specification, but that's basically all it's saying is that it's the minimum of those two. If you take this and look at the two rows, you'll see that there's a lot common. So for example, if you have an equation, right, and you're saying, I want to find the minimum of x plus y and z plus y. Really what you're saying is it's the minimum, it's y plus the minimum of x and z. So we can factor out that UBS, FU, A, and T term, and then we recognize that both of the remaining terms have a 0.6 next to it, so we factor that out. So basically what's in gray versus what's in yellow, it's the same math, it's just making the calculations a little easier from a number crunching standpoint. Either one will give you the same answer. If you look at the expression, a lot of the terms they should be familiar, things like the yield stress and the tensile stress. We have not yet computed things like gross area and shear, net area and shear, gross area and tension, net area and tension. We haven't computed that stuff, but it follows the same principles that we've been talking about so far. One thing I'll mention is if you actually get into the equation, you actually won't see an AGT term anywhere in this equation. You'll only see the net area and tension. But you can't compute the net area and tension without having the gross area and tension first. That's why we list them all, because you need all of them. We have a block shear reduction coefficient. Again, I'm going to just very quickly highlight that because for us, it's going to be 1 in every case that we handle, so we're not going to really need to talk about that. And then the phi value is 0.75. Okay. As I said last time, there is a 0.6 attached to the terms that are related to shear. That 0.6 is not a safety factor. It's not some, let's just throw it on there to be safe. It is an actual representation of what's going on when you take an element of steel and subject it to pure shear. If you take an element of steel and subject it to tension, it will yield when the stress hits Fy. But if you take an element of steel and you subject it to shear stress, it won't yield when the shear stress is Fy. It yields when the shear stress is Fy over the square root of 3. Now 1 over the square root of 3, if you plug it into your Casio FX115ES Plus, you will find that it's about 0.5774, and the steel manual just says, what the heck, let's just round that up to 0.6 for simplicity. But again, it's not a factor of safety. It's representing what's actually going on. Like if you were to take a piece of steel in the lab and load it in shear, it will yield at a lower stress. And again, UBS for us is going to be 1. There's only one real case where it's lower, and that's if you have multiple rows of bolts on a coped beam. One of the things I do want to say one thing though, just off the side. Okay. Steel behaves the way that steel behaves, okay? And the truth is, we do have a pretty good understanding of how steel behaves, and a lot of the models that we use in the specification are pretty good in capturing or predicting behavior. But there are some things in the land of engineering that we could be better at, okay? One of the things that you will find maybe in the next edition of the manual, so we're in the 15th edition, maybe in the 16th edition, there are better predictions and better means of computing things like UBS. Personally, I don't think this is going to change anytime soon, but maybe in a later edition, maybe it's not 0.5, maybe it's 0.6, or maybe there's an equation that's used to predict UBS because somebody went and did oodles and oodles of tests in the lab and used abacus and all sorts of different research techniques to find that there's a better way of computing it. The point I'm making is that, I don't want you to get married to this value being the UBS value for the rest of your lives. Stuff might change, okay? I want you to understand the context and the behavior, but just recognize that specifications change because we get better at engineering. Like we learn about the results of our design and our processes, and we do better moving forward. So just make sure that you're adaptable to change, is what I would say. Okay. This is kind of what I want to discuss a little bit about before we get into the example today. But I want to talk about identifying block shear failure tests. Okay, so I brought a marker today because look at me, I'm prepared today. But what we have, so I'm going to draw this here on the screen, okay, or here on the board. But I'm not drawing anything here on the board that isn't on the screen, so it's not that too big
I
of a
mean,
deal.
you can draw it on the screen. People do that.
I'm not gonna do that.
I've never.
Unlike some professors,
I've never
that was
seen
for-
any.
That was for the YouTube recording, so.
I've never seen any of my professors do that.
No. He'll get a kick out of this one, I'll tell him that. All right, so here's this connection scheme. Okay, so we're talking about block shear. Okay, so let's go back to the basic definition. Block shear is a path that contains both a tensile failure and a shear failure. Okay, so if here's the member, and I'm yanking on it with some load like this, I'm yanking on it this way, any path that's in this direction, that path is going to experience tension, right? Because if like for example, this is a potential failure path for the member, right? That's net section fracture, right? Because what's happening? You're yanking on the member in tension and it's failing along this path. So tensile paths are going to be perpendicular to the load, whereas shear paths are going to be parallel to the load, okay? So let's go back to our rules for identifying paths in block shear. Okay, the first thing that we need to recognize is that all the bolts need to be intact. Okay, so like as an example, okay, this would not be a viable block shear failure path. Okay, because let's say for the sake of discussion that I were to rip this block off of the tensile member, or the tension member. So let's rip this off. And let's say this is my tension member. The problem is that the tension member is still attached because there's bolts here. The only way to separate this member from whatever it's subjected to or whatever it's connected to after this fails is to shear these bolts. Does that make sense? So whatever failure path that you identify has to basically encompass all of the bolts that are in the connection. So that path that I just drew is not a viable path. That's not viable. Okay? So let's talk about one that is viable. Okay? One path that is viable is this, right? This is a viable failure path because if I were to take the connection and I were to cut this out and say that here's what's left, there's nothing left connecting this plate to the adjacent member and the plate will freely fly off. Does that make sense? Is everybody okay with that? So it needs to leave all the bolts intact. It needs to separate the member from the connection, and it does have to include a path subjected to shear. Okay? And what that last bullet means is this, is again, here's the connection. Right? A possible failure path for this member is again this. Like that is a possible failure path, okay? Because I could fracture along this line and completely separate the member. The problem is that's not block shear, that's just net section fracture. So it wouldn't be relevant towards the limit state that we're trying to look at right now. Make sense? Now this is for a plate, okay? Now the point there's a couple points I want to make with this slide before we move on to my little animations, and that's this and this, okay? Okay? I want to look at this block, and I want to look at this block, okay? So, here's this block, and here's this block. Now, theoretically, we could do a block shear calculation for each one of these and get an RN or a phi RN for each block, okay? But I want to put our thinking caps on and let's start asking ourselves which one is more likely based on our connection. Which one is more likely to govern? Well, we can do both, but I do want you to put a little bit of your thinking caps on. This path is subjected to shear, right? This path right here is subjected to shear. And this path right here is subjected to tension, right? What about right here? This path is subjected to shear. This path is subjected to tension. So, looking at these two, which do you think is stronger? This block or this block? Block 1 or block 2? Let me ask it a different way. Which block has more material that I got to rip through to fail it? Block 1 or block 2? Block 1. Guess what we're going to say?
I was gonna guess block 2 would be the stronger.
And the answer is no, okay? And here's why. I've got more material I have to rip through with this, right? Because imagine that this is, I don't know, 6 inches long, right? So my gross area in shear here on block 2 is going to be 6 inches times whatever the thickness is. But for here, the gross area in shear is going to be 12 inches times whatever the thickness is. Y'all see what I mean? So that's more material I have to fail through, okay? So that's what I'm getting at, where I'm saying it kind of makes sense that the block shear path that's going to govern is the one that has the least area that you're going to rip through. All right, let me give you some more concrete examples that might be a little easier to wrap your head around, okay? So this is AutoCAD or Autodesk Inventor, okay? So what I have here are a couple of examples of block shear failure paths, and we're going to talk about why they look the way that they look, and you'll kind of get an understanding for what's going to govern and what's not. So let's start off with this, okay? So this is actually going to be representative of the example that we're about to do in class today. This is an angle, okay? And it's an angle that is bolted on one leg, okay? Now I propose that based on this, and this is drawn to scale, okay? I propose that the governing block that we're going to need to check is what we're seeing right here, okay? Now let me throw up 3 potential blocks. There's actually more than that, but let me throw up 3 to try and illustrate why the others wouldn't govern, okay? So please forgive my 3D artwork. Okay, is that okay? Let's do one more. Okay, so the one that I have illustrated is this, something like that. And so I propose that the only thing that's in shear is this path right here, and this is the path that's in tension, right? Okay, now here's another failure path. Another failure path could be, okay, so it's got to surround all the bolts. It has to include a shear path and leave all the bolts intact. Well, what about this? Actually ripping all of this part out. Is that a viable block shear failure path? Yes, according to the rules. Is it going to govern? No. Okay, here's why. Okay, think about the gross area in shear. I propose that the gross area in shear for block 1 and block 2 are exactly the same, right? And as we're going to see, the net area in shear is the same. But what happens with tension? With tension, I only have to rip through that small amount up here, whereas in block 2, I got to fail through all of that, right? That's just not as likely to occur. Does that make sense? Another path, which is equally ludicrous, but I mean, I guess is possible based on the rules that I've defined, is we could have 2 blocks. We could have a block that rips out like that. We could rip this part out, and we could rip this part out. That would satisfy my rules, wouldn't it? But is it likely? Of course not. Not for this, right? I mean, think, if I were to erase those blocks from this angle, I would fully separate the connection, I would include shear paths, and include tensile pads and leave all the bolts intact. But that wouldn't be realistic, right? See, what's going to happen is with this, I'm going to have 2 paths in shear, so my gross area in shear is going to double. I've got all this material and tension I got to fail through. This is very obviously the weakest block in this scenario. Does that make sense? And so what would happen, here's the angle, what would happen is I would fail like that. Does that make sense? Now, one of the things that's going to be kind of interesting, and I really kind of like the schematic, is the net area in shear. So I propose the gross area in shear is this whole path right here. But the net area in shear is this rectangle, this rectangle, this rectangle, this rectangle, all that. Like that's the net area in shear. Now I'm curious, if I have the gross area in shear, and then I want to compute the net area in shear, I take the gross area minus the area lost due to the presence of bolt holes. How many bolt holes do I subtract? 3. No. No. No.
It's like 3
Say it
or
again.
4.
Who said it?
3.5.
3.5. Because here's the path, right? Right, so I've got 1, 2, 3, 4, and the block goes like this, right? So I subtract 1, 2, 3, but a half because it goes to the center. Does that make sense? Does everybody see that? So whenever so we're going to see this here in a bit. Whenever you do block shear failure paths, a lot of your hole subtraction aren't a hole; it's a half of a hole, like 3.5. How many holes would you subtract for the net area in tension?
1.5.
1.5. Does that make sense? All right, good. I'm glad because that's again, it's one of the reasons why I kind of like the schematic here. All right, make sense? So let me give you another example to kind of visibly see this. Here's a channel, okay? And I propose that for the channel, this is about the most viable failure path that you can see, okay? Because the other potential failure path would maybe try and rip through all of this. But I think looking at the area, I think you would see it's probably not as feasible to rip through the main body of the channel instead of just ripping through the center part here, okay? What about wide flanges, okay? Wide flanges connected via the flange have a very interesting way of failing. They fail like this, okay? So what happens is, I'll do this free move here. What happens is, again, we have to fully separate the member from the connection. What we do is we just have these little bits that rip off of the end, and we separate the connection like this, okay? So the way that we'll handle block shear calculations for a situation like this is we'll just look at the capacity of a single block, and then for the entire member, multiply it by 4. Does that make sense? Everybody okay with that? And again, for each block, so let's look at this. How many holes do I subtract for the net area in shear for a block? 1, 2, 3, and a half. How about for the net area in tension? A half a hole. Does that make sense? And so that will give you the capacity for a single block, but in order to fully separate the wide flange from the connection, there are 4 blocks that we have to rip through. So what we'll do is we'll compute the block shear capacity for a single block, then for the whole member, just multiply by 4. Does that make sense? Everybody kind of see that? Let's do some math and solidify that. So let's go here. All right. So here's the member that we're going to do. We have an L6 by 4 by 5/8, and it's to be used as a tension member. We have 1-inch diameter bolts that we're using, okay? And we're going to determine the design capacity of the angle according to block shear, okay? So let me pull this up on the notebook because some of these dimensions might be a little small to read. It might be a little easier if I pull it up here. That might be is that a little easier to read? So just so you're aware, and here I can probably put this here on the screen, this is an angle that is connected by its long leg. Okay? So So what we have is an L 6 by 4 by 5/8. So the 6-inch leg is what's being connected, right? So one of the things I'll mention off to the side is that this is an unequal leg angle, right? Right now we're looking at block shear, but what if we were looking at net section fracture? We would have to look at our shear lag tables in order to evaluate case 2. Case 2 is what, 1 minus x bar over L? Which one do we use? Do we use x bar or do we use y bar for the angle? We use x bar. X bar is the connection eccentricity from the long leg to the centroid. Y bar is from the short leg to the centroid. Okay? We've been doing with equal leg angles up until now, so it didn't matter what x bar or y bar we used, they were the same. So far so good? Alright, so let's do a little bit of initial work. We need A36 steel. A36 steel has an FY of what and an FU of what?
36 and 58.
There we go. All right. And we're gonna make a point here in a second, but we'll get to this. For the angle, for block shear, the only thing that we need is the thickness, okay? And the thickness of this is 5/8 because it's an L6 by 4 by 5/8. If we want to evaluate gross section yielding and net section fracture, we obviously need more properties, but we'll get to that here in a bit, okay? Now, we also need for the bolts, we have the bolt diameter is 1 inch. So what does that mean for our hole diameter? 1 1/8. All right. Okay. So now what we need to do is we need to assess the block shear capacity. And in order to do that, the hardest part is computing the areas. Okay? So what I'm going to do is I'm going to redraw this a little bit. Okay. All right, and then we have okay, so we have this, all right, and our block that we're going to rip through is going to be this. That's our failure block, okay? Now, can somebody tell me what this dimension is?
Ten and a half by 4.
10.5, and this is 4 inches. Bless you. Let me ask you a question. For shear lag, is the connection length 10.5 inches? It's 9 inches, right? Because for shear lag, we go from outside bolt to outside bolt. These are the little details I want to make sure that you all are aware of when you start going into celebration land, because you got to make sure you got your details oriented. Wait. Hold on.
That's not 4 inches.
No. Wait, yeah, I think this is 3.75. Let me see. Hold on. Do I have a typo? Let's see.
No, that's right.
I might have wrote.
No, yeah. This is 1 1/4. Yeah. Sorry.
1.5.
All right. Now, in order to calculate block shear capacity, the hardest thing to do is to calculate your areas. Okay. Now, I can tell you we know that UBS is going to be 1, so we don't need to worry about that. But we're going to need to calculate a gross area in shear, a net area in shear, a gross area in tension, and a net area in tension. Okay. So let's start off with the gross area in shear. Okay. Now, to be clear, we are yanking on this way. Okay. So this is our shear path. This is our tension path. So somebody tell me, how do we compute the gross area in shear? What do we do? So an area is just length times the thickness. Yes, sir. Go ahead. So
Is it just the length of from the end of the bolt to the other bolt times the thickness?
yep, and so that's
Of the full length.
well, no, it's going to be the whole length because we've got to rip through all of it. So it's going to be 10.5 times 5/8.
6.56.
We'll say 6.563. Right?
Yep.
Because to be clear, right? Right? If we're talking about a path, right? We're talking about this block. Like that's what we're ripping out, right? So when we're talking about the gross area in shear, we're talking about the area of that rectangle. That's what we're talking about, right?
Come on, a slice.
What's that?
A slice.
Pretty much, yeah. So the gross area in tension is going to be the area of that block, right? But we'll get to that here in a bit. Now the net area in shear is going to be the gross area in shear minus how many bolts? 1, 2, 3 and a half, right? So that's going to be that. So what do we get for this? 4.1. Okay, I got 4.102.
Yeah.
Does everybody else get that?
Yeah.
Okay. Now what about AGT? What do we get for AGT? So AGT, we're talking about this area here. So it's going to be 3.75 times the thickness. And what is that?
2.344.
Okay. And just so you're aware, again, I'm going to like 3 decimal places because when we do the math for the formula here in a bit, I just want to make sure everybody sees where all the values are coming from. All right. And then finally, ANT is going to be AGT minus how many bolt holes? 1.5. So what do we get here?
1.289.
Okay. Is that hard? If not, then everything we're about to do is going to be pretty rote. Okay. So what I'm going to do over here off to the side is I'm going to do a calculation. Tell me what FY AGV is. It's 36 KSI times 6.563 square inches. Tell me what that is.
236.268.
Second? All right. How about FUANV? That's a 4, not a 9.
$237.9.
237.9?
Yeah, 0.916. Wouldn't go that far.
Okay. All right. Everybody okay with this? All right. So here's why we did that. Okay. So our expression for the nominal capacity in block shear is UBS FU ANT plus 0.6 times the minimum of FY AGV and FU ANV. But we did these off to the side. So which one's the minimum? The top one, right? So this one's the one that's going to govern. So this is going to be 1 times 58 KSI times 1.289 plus 0.6 times, and we'll just say 236.268 kips. And so when we check this out, what do we get?
I got 216.52. You want 3 decimals?
We'll say 216, we'll say 2 decimals. What did you say, 216?
Yeah, 216.52.
Do I have a second on that?
Yeah.
Okay. Is that our design capacity? Did I forget something? Probably. My what? What did I just compute? I computed RM. This is LRFD, ladies and gentlemen. I need phi RN. Phi RN is 0.75. Easy to forget that on a celebration of learning. So for block shear, phi is 0.75. So remember, gross section yielding, phi is 0.9. Net section fracture, phi is 0.75. For block shear, phi is 0.75. So what do we get for phi RN? And we'll say 1 decimal place on this is good enough.
162.4.
So that is this member's design capacity, okay? Under block shear. Now I want to make a point about something, okay? Let's see how much time we got. Oh, we got plenty of time. I like it. those problems we've been doing up until now, we've only considered two limit states, gross section yielding and net section fracture, right? So, now we got a third one. So, remind me, we compute gross section yielding by taking 0.7, or no, 0.9 Fy Ag. This is 0.75 Fu Anu. And block shear rupture, we just got 162.4 kips. So could block shear rupture govern? I don't know. How about let's look at a simple one, gross section yielding. Gross section yielding is 0.936 KSI times, what is the gross area? Somebody tell me what's the gross area for an L 6x4x5/8?
5.86.
5.86. Or inches squared. What is that?
I got 189.86.
So if I was looking at this capacity and this capacity, which one's going to happen first? Block shear. Does block shear govern overall? Well, I don't know. We have to check net section fracture, right? How would we check net section fracture? Well, we'd have to compute the net area. Which is the gross area minus, if I was calculating net area for this problem, how many bolt holes would I subtract? 2. So, all right, so gross area minus 2 dE times T, which is 5.86 inches squared minus 2. What is that? I don't even have this calculated, previously. Like, I genuinely don't have this one. Sometimes I'll lie and I'll say I don't have it when I actually do. No, I actually really don't have this one.
I got 4.45.
Do I have a second on that? Okay. All right. Shear lag. Shear lag, I believe, for this member, we're going to have to consider either case 2 or case 8, right? Because we have 4 or more fasteners per line in the direction of loading, right? So U2 and U8. U8 is going to be 0.8, and U2 is 1 minus X bar over L. Now, 1 minus, we know that the connection length is 9 inches, right? What is the X bar for an L 6x4x5/8?
Inches.
So what's 1 minus 1.03 over 9? 1 minus 1/9 almost, 8/9.
How many decimals do you want?
3.
0.886.
Second. So of these two, take the max. So So, what do we get out of this?
I got 171.51.
Do I have a second? So if I were to yank on this member, looking at gross section yielding, net section fracture, and block shear, what governs? Block shear. It would actually fail in block shear before it would fail in any of the other modes, because its capacity is the lower, right? So it's interesting. So this is the type of member that would definitely, like, it would probably require some iteration on design, because I can imagine that our design process designs for gross section yielding and net section fracture, and then we check block shear later, and we find that block shear governs, right? One of the, as I mentioned before, I said that one of the reasons that you might have to iterate a lot is if you have really big bolts, because they have a big impact on your net area, which is what happened here. So yeah, interesting stuff. Any questions? Yeah.
How much impact does the torque on the bolts have with regards to the formulas that are used?
None yet. It will. So the short answer is there are two classes of bolted connections that we use in structural engineering. One is a bearing type connection, and one is a slip critical connection. And slip critical connections are ones where we count on the friction generated between the plates. But in order to use a slip critical connection, you have to use a very specific installation technique. And we're going to talk all about those here in a bit. So it doesn't affect tensile member capacity, but it's going to have an impact later. So if you use slip critical connections, you end up having to use about twice as many bolts. There are two real areas where slip critical connections get to be really important: bridges and earthquakes. But we'll get to that. We'll talk about that later. But short answer is it will have an impact.
I was thinking more on, how it might impact the strength of the metal, the thickness of the metal, depending on how it's torqued, but I agree with you.
It'll be easier to answer that question a little later, so I'm going to put a pin in it, but I want to come back to that when we get to these limit states. It might. So that's the best answer I can give you now.
Not there. You're welcome.
Any other questions? All right. I'm going to pull up the code again, but that's all I got. I'll see you all on Monday.